Hello, I'm David. I'm the coordinator of the Maths Learning Centre at Uni of Adelaide. This semester 2, 2023, and this is a revision seminar for Stats and Numerical Methods. I've already warned everyone here, I'm still learning some of the things about stats and numerical methods. So some of this will be making up as we go along. Just bear with me, but most people find it helpful. Okay. Someone has asked about the big O, and I might as well try and get that out of the way a little bit and then move on. Because there was something that someone asked in the Maths Learning Centre just a few days ago that I think is worth talking about. Okay. Big O sucks, honestly. Like it's a terrible notation, but here we are. And one of the reasons it's terrible is that people in different disciplines use it differently. For example, computer science versus maths. So if you're studying both of those, you're going to have to code switch to know what they're talking about. But in maths, big O is about how quickly something shrinks when you make the input smaller. And the reason I say it this way is because you've seen a couple of different contexts where they ask about big O that feel different. So sometimes they'll give you something like this. Oh, crap. Which direction does this go in? Well, let's just do it this way. And they draw a graph something like that. Maybe I don't want that graph. Anyway, we'll run with it for the moment. So this is a graph that's trying to indicate, based on the size of the input h, what is the size of the error? And it's usually about errors. That's the entire vibe of the numerical methods part of this course. It's like, we don't have the actual function. All we've got are particular values. If we attempt to calculate derivative, integral, solution to differential equation, whatever, how off could we be from whatever the correct answer is supposed to be? And so that's the whole vibe of numerical methods is that, as far as I can tell. And so as this h gets smaller by 10, so does the error. Like it's 10 times smaller going from 10 to the minus 4 to 10 to the minus 5. And it's 10 times smaller going from 10 to the minus 1 to 10 to the minus 2. And so this is big O of h to the 1. So the slope of this is 1. Like slope of this in the logarithms, the slope of the powers. Like this is a log-log graph. So officially, the gap between 10 to the minus 6 and 10 to the minus 5 on an ordinary graph is 10 times smaller than this gap is on an ordinary graph. So what they've really drawn here is actually something more like log of h on this graph. And Oh, that's a -2. Crap, that's supposed to be a 3. Log of the error on this side. So if you're ever in a situation where you're not in an exam and therefore have a computer to draw things for you, it's usually much quicker if someone gives you a table of values for the error and the h to calculate the logarithms and draw them and literally find the slope of what you've got. So the slope in the log sense is 1 because we're going, when I go up 1 here, I go up 1 here, and therefore it's big O of h to the 1. And all I'm going to say is don't turn off your natural reasoning skills that you learned in year 10 when you first did slopes and graphs and stuff. You're still going to use the same reasoning to figure out the slope of things. So if you've got a graph that goes like this, something like that, then you're going to need to find the slope of that line. So choose convenient points. So you could choose these two, but it's hard to read what the numbers are. These two are on grid lines, so I'm going to use that one. And so for every one across here, it goes up that much, which is a little bit more than 2. Yeah. Because this gap is from -4 to -2. And so this is 1, and this is a bit more than 2. And so I'd probably make a good guess that it's big O of h cubed, probably. About right. The slope is nearly 3. Yeah, maybe it was like that. It's about halfway. Something like that. Make a good guess at what the slope is and just run with it. You're supposed to pick a whole number traditionally, yes? What do you mean by that? They'll usually make it really obvious for you, the people who are doing this for you. In real life, it's totally okay to have like 2.5. Nothing wrong with that. It's just a bit weird. Yeah. But if you are doing things like Taylor series and that sort of thing, it will be a whole number. And so pick the nearest whole number is what I'd say. Yeah, so maybe it's going to guess it's 3. I drew a bad graph because I didn't have access to the one that I was helping someone with the other day. But that's the general idea. It doesn't have to be the beginning and the end. It doesn't have to be 2 of them that are next to each other, just whichever ones you can figure out the slope from, and that's what you can do. And if you don't have a graph, you can figure it out from that too. Oh, this one's going to take me a little while longer to... Okay, this is my table. And I ask, what's big O of the error? And so you need to know how the error changes when the input changes. And it has to be about multiplying and dividing. It's about dividing by 10 or dividing by some other number consistently. So you can make a pretty good guess at what the big O is going to be just from staring at the 10 to the power ofs. These are going down by 1. So it's about dividing by 10. Not quite, but nearly. And these are also going down by 1. So it's big O of h to the 1, maybe, but we'll just have to figure it out. It might be big O of h to the 2. That's about where it is that we're thinking about. Because it's not quite dividing by 10, because dividing by 10 would be 6.2 times 10 to the minus 4. That'd be dividing by 10. So it's dividing by something a little less than 10. All right. We can figure out how much it divided by going this divided by that. Well, this divided by that would work. That would be nice. So we want to know, what did we divide by here at each step there? So if this divided by something equals this is the same, just a second. And to figure out what that is, we could times it on this side and divide that. Okay, so the thing is therefore this, just to be absolutely clear that I know what I'm doing here. So, all right. 7.75 times 10 to the minus 4 divided by 6.2 times 10 to the minus 3 is, just a second. Did I do that wrong? That doesn't make sense to divide by that. Maybe I didn't put brackets in right. Right, just a moment. Oh, okay. This is not what I thought I did. Just bear with me. I just need to think it through. Oh yeah, it should be that one. The big one divided by the small one will tell me the number I divided them. Okay, sorry about that. Oh yeah. I know why I did my algebra wrong. That went up there and that went down there. And so that would be actually the question mark is the 6.2 times 10 to the minus 3 divided by. That makes sense. Okay, cool. Much more sense. Eight. Ah, it's almost like I set it up that way. I told you it was a little bit less than 10. And let's just check if the next one works. (10.75) times 10 to the minus 4 divided by 9.7 times 10 to the minus 5 is 7.99. That's pretty close to 8. So I reckon we're dividing by 8 each time. If I go back to my table, I'm dividing by 8. Let's just see what happens when we divide this way. 5.8 divided, sorry, 5.8 negative 2 divided by 9.1. What? That's supposed to be 9.1. Ah, interesting. 63.73. What's this one? Damn it, wrong way around. Ah, you can tell I don't use a traditional calculator very often. 65. Okay, it looks like it's about 64, which is 8 squared. So successive errors. I don't even know how to show the working for this. So since this is nearly that squared, it's big O of h squared. That's the idea behind it. Yeah. So dividing this by 8 is the same as dividing this by 8 squared. That's the idea of what big O is about. So since h divided by 8 produces error divided by 64 and approximately, and 64 is 8 squared. And so therefore we're going that the error is big O of h squared. That's the idea behind it. Going to stop for a second. How's that feeling? Back a bit. Okay. So that's what those things there are sort of qualitative. That's what they would mathematicians call it, qualitative ways of making sense of how the error works. As the error shrinks, the h shrinks, the error shrinks as well. What you really don't want is the h shrinking, the error growing. That would be bad. And you don't really care about h getting bigger and the error getting bigger. It's more the other way you're interested in. If you want to know if something's big O of something from an algebra point of view, this is like more of a Maths 1B thing, but like, you know, approximate. You know, root 1 point. No, just bear with me. Taylor polynomial, degree 3. Do they call it size? Do they call it the order? They just did a say what's the big O order? Oh, that is fuzzy. Sorry. There we go. And I happen to know what the Taylor series of this is, so that's great. And so you'll get like P3x is like minus a half, half times minus a half, 3 halves. Pretty sure it's this. And then there'll be an error term, right? Which will have crap times x to the 4. You know, there'll be a fourth derivative of at some number t divided by 4 factorial, something like that. That's right. I should have said Maclaurin because it's a center 0 if I'm writing it this way. So the thing is that this is the error here. It's how far the, sorry, crap. F of x is equal to this plus this bit on the end. And that bit there is the Taylor polynomial. Right. Just going to stop for a second. Reset. Okay. When you do Taylor series, you start with all the derivatives and stuff. And you sub them in at the center and you get this thing. And I will talk about this in more details in just a second. And you get the thing, and then there's an error term at the end, which is always like the next derivative at some position which is not the same as x, times x minus whatever to the power of the next power. And so this is the error here. And look, it's got an x to the 4 in it. It's big O of x to the 4. That's it. That's pretty much the deal. So if you get at the end a term which has an h to the 4 in it, as your error, it's big O of h to the 4. That's much simpler than this other stuff, but this is the idea behind it. So there's two ways of thinking about it, at least. One of them is, well, Taylor very helpfully said to us that there is, for every x, there is a t that makes this work. And as long as this function here is bounded and this doesn't get any bigger than any particular thing, then this whole thing's less than or equal to constant times x to the 4, and cool. And constant times x to the 4 is big O of x to the 4. That's the idea behind that. So we've got one idea is, as long as is less than or equal to constant for some c. So maybe it's like sine or something, and it's always less than 1. Or maybe you only care about x's that are within the zone of 0 to 1 anyway. And so as long as there's like a maximum for what this could be, then error is less than or equal to some constant times x to the 4, which is big O of x to the 4. I'm not sure if I'm allowed to use equals here. The computer scientists are pretty free and easy with what they use equals for. Mathematicians may want to use an in sign. I don't know. It probably doesn't matter. Which is big O of x to the 4. That's one idea. It's like saying, look, I don't really know what the formula is for figuring out the correct value of t, but it doesn't really matter. It's always less than this. And so bounded by x to the 4. The other idea is, if you did the entire full Taylor series, like 1 plus x to the minus 8 x squared plus a 16th x cubed plus something times x to the 4 plus something times x to the 5 plus forever. If x is a nice small number, like say, a tenth, like 0.1, then x to the 4 is 0.0001, and x to the 5 would be 0.0001, which is even smaller than this is. And the next one would be even smaller than that. And the next one would be even smaller than that. And so the size of this error is really dictated by that first term. Because if x is really small, then x to the 5 is smaller than x to the 4, and so is x to the 6. And all of these later ones are smaller than this one, and so they don't count so much. Especially if x was 0.01, then x to the 4 there'd be like, 8 zeros, and x to the 5 there'd be 10. And the smaller you make x, the even smaller again the x to the 5s are than compared to the x to the 4s. And so as x shrinks, these things will just be, who cares? They'll be so small it won't make a difference. That's the other idea behind it. So you're used to, with polynomials, the big powers telling you what to do. But that's because when you talk about the leading coefficient of a polynomial, you go, oh, cool, I go to the biggest power, and that coefficient tells me whether the graph points up or down, right? But that's thinking about what happens when x is a really huge number. we're wondering about what happens when x is a really tiny number, and so it's the small powers that lead what the graph is doing, not the big powers. How are you feeling? That's all I know about it, really. They're the two ways of dealing with it. If you've got literal numerical information about how the error changes when h changes, then find what you divide by to get from one h to the next, and see what power of that, the one error to the other. That's this thing here. Go like this divided by that, and see how much you went down by. Go this divided by that, see how much you went down by, and hope that this is the power of that. And the other way is algebraically to, find something that involves the x or the h or whatever you're interested in, and say, well, the biggest power in that error is this. Sorry, the smallest power, and therefore the biggest value when you sub in a small number is this one. Yeah. So from an algebra point of view. So there were several assignments along the way that had things like, here's some wicked, weird formula that approximates the second derivative. Show that it has error of whatever. Did you want to do one of those? Or are you happy for me to skip it? Because I did do it last year. Cool. Awesome. I did do it last year and probably the year before, actually. So I might just skip that. But I will just say one thing about it. It's all based on Taylor's series. So the idea is that even if you don't know what the function is, Taylor series goes like this. Oh, 3 factorial x minus c cubed, and so on for as long as you need to go. Yep.
Is it always the fourth term that you're subbing t into?
Not always. It's whichever term gives you the correct power of h that you're going for. So, yeah. So if they tell you in advance to show that it's big O of whatever, you want to go at least to the fourth term. But if your formula, sorry, if your formula had like something like that, all over h or something ridiculous, then thinking about what the Taylor series is going to do, the Taylor series for this one is going to produce an error term with an h to the power of something. And the Taylor series for this is going to produce an error with an h to the power of something. And that h to the power of something is going to be divided by h. So if you want it to be big h to the power of 4, you're going to need to go to the fifth one so that when you divide by h, you end up with an h to the power of 4. That's my reasoning. Yeah. So you need go to error with an h to the power of 5 so that when you divide by this h, you end up with an h to the power of 4. That's my, currently, that's my heuristic. If they didn't tell you what the h to the power of what was, go a little further than you think is necessary and see what happens. That's all I can suggest. I'm really sorry. Leave enough space in your working to put an extra term in there in case. Yeah. And this is just want to point out that I have no idea what the big O of this would be. I'm just making up crap. Okay. But it is all based on the thing. And so if I stopped here, I would have F4. Maybe I'll go to the next one. And then there'll be F5t over 5 factorial x minus c to the 5. And the thing that's really important to know is that you pick your center to be one of these x's that goes with this. And it's normally like this. And the distance between them is h. So that you can now put, instead of c, you can put the xj. And then every time you have xj plus 1 minus xj, you can replace that by an h. Yeah. There is more than one way of doing it. Video shows several ways if you want to try them. Yep. Also, so do your assignment solutions. I mean, but the video has my thoughts that go around that, so that might maybe help. Yeah. Okay. Damn it, I missed that chat thing, and now I don't know what question that yes is answering. It's probably, are you okay with me moving on? I'm going to just pretend that that is what it's. Okay. What next? Sounds like people really do have feelings about the statistics. So I might talk about that for a little bit. I may get back to some of those LUs and stuff. Yeah, after I've had a little break in a minute. Okay. Right. Well, it's big heading stats, but we'll deal with some other things along the way. So some people have highlighted something really important about statistics, which is what a lot of people make people worried and annoyed about statistics, which is you're constantly having to choose which thing to do. And you constantly feel like there's information that the lecturer has about how to make that choice that they're not telling you. And they're not deliberately trying to be annoying about that. It's partly because they don't know how they make their decision. They just do. I mean, they do, but they've forgotten how they do it. Yeah. Some people call in education research call this a threshold concept. Threshold concepts are concepts that you don't know are there after you've learned them. Things like the fact that things fall downwards is a thing you have to learn when you're a baby, and you don't remember it as a thing that you learned now. It's a threshold concept. Everything that you expect about the way the things move in the world is based on that concept, but you don't remember that it's there. So cut them some slack. They're not deliberately being annoying. They just are being annoying. So yeah. And there are so many places, and people have mentioned them already, that there are choices, right? So how do you choose whether you're doing a normal or a t-value? How do you choose between a chi-square or a t-test or a paired t-test or a whatever? And actually, you'll notice that almost all of the problems in all maths courses are about how do you choose. They're one of the most difficult things for people to describe to you. And that's some of the things we try and give with the revision seminars. So just letting you know, it's not just you, okay? It is a feature of how learning works that it's difficult for people to describe how they choose things. But it's also a feature of statistics. There are many choices. And statisticians love making those choices. Gives them a thrill. They also misunderstand how learning works in the sense that you actually do have to tell people how choices are made. They think it's obvious. They just give you enough of those choices. They think you can abstract from that the features that you're looking for that make the choice. But there's so much going on in those problems, you can't tell which bit is which that tells you what the decision was. So I'm going to try and focus your attention to help you with that. And hopefully we can talk about normals and T's and stuff. Yeah, and we'll get there. Okay. So I'm going to do two of them, which is distributions and stats tests. So, brainstorm, what probability distributions have you seen in this course? Feel free to call them out. So we've got, I'm just going to put a heading here. So we've got some terminologies. We've got continuous and not continuous. Does anyone remember what the word for not continuous is? Beautiful. Okay. There are some distributions with names. I'm going to give you one, the binomial distribution. Can you tell me some others? That's what you were saying? It is pronounced poisson because it's French. And in French, the OI makes a wa sound, just like in moi or croissant. OI makes a wa sound. So this is pronounced as poisson. Yeah. I mean, officially it's poisson. You don't say the N either because that's French. You never say the last letter of any word. Anyway. Any others? Sorry? Oh, Bernoulli. Fun, fun, fun. Standard normal. Oh, uniform. Oh, there's so much fun. I've forgotten how many there were in this course. Oh, cool. T. Anything else? You have to help me remember what's in this course. I have some suggestions. There's definitely a chi-squared because you've mentioned it already. It's called F. Yep. F for Fisher, who invented it. No, it's just called the F distribution. I have heard at least one person once call it the Fisher distribution, but it's just called the F distribution. Z is one, and that's the standard normal. Good. Oh, that's interesting. That's not something I remember, but let's just write it down just in case. I mean, Euler turns up all over the place in this course. I don't think Euler is one. It may have turned up in one of the assignments just because they wanted to give you a random distribution, but they don't really want you to remember it forever. I think that's pretty much it in this course. If we think of one later, we'll add it to the list. That's a lot of distributions. So this is different here. These terminologies are kinds of distributions, and distributions come in those two flavors. So continuous distributions are these ones. They're all continuous. What does continuous mean to you? Well, that's a great way of talking about it. It is almost always true that continuous distributions come about by doing measurements, but sometimes they come about by doing calculations. I just want to point that out. The t, the chi-squared, and the f, you never see them in the wild. They're only produced by doing calculations for the purposes of doing test statistics. The other kind of distribution is discrete. And these are all discrete distributions. There's only 3 of them with names in this course. Say something about discrete distributions, what that means to you. What did you say? Actually, you can count it. You can only count it. In general, a discrete distribution can only be whole numbers. It's not technically true. A discrete distribution just can only be certain numbers. But these ones can only be whole numbers, so it's good. And they tend to come about by counting things. The official definition is that a distribution is discontinuous when no matter which 2 values you think of that are possible, there is always another one between them that is also possible. Which is the definition of continuous for functions too. There's always a function value between them. So yeah. But in general, discrete things come about from counting something and continuous things come about from measuring something. Okay. I'm just going to put here, there's always another number in between. But with discrete things, you get down to a point where there's no number in between them. You go, cool, I'm counting how many lightning strikes there were, and I've got to put the number 1 and the number 2, there is no number in between them. Just, yeah. Okay. That's the decision making between discrete and continuous. But it's a useful categorization because it tells you in your situation that if you're counting things, you've only got a small number of options for what it could be. Okay. How do you feel about that? Cool. Just going to make sure I've numbered my pages so that I don't lose track of what's going on. Okay. All right. So you have to know, unfortunately, you just have to know some things about the kinds of situations that certain distributions appear in. I'm going to just talk about the Bernoulli, the binomial, and the Poisson. I'll line them up next to each other. The Bernoulli and Poisson are both named after people. Bernoulli was Swiss, Poisson was French. Or maybe he wasn't. Anyway, his name's French, but Bernoulli was definitely Swiss. I looked him up yesterday. And binomial is not somebody's name. And there is no person called binomial. It is a description of the algebra theorem that produces the numbers mentioned in the Pirates of Penzance, in case you didn't know. Gilbert and Sullivan musical. Anyway, so each of these and all of these are discrete because they're all counting something. The binomial distribution counts how many times a thing happens when you do it a particular number of times. Counts the number of times an event happens out of a specific list of trials. And it's very important to notice what that means is you've got a trial and then another one, and then another one, and then another one, and we're asking yes, no, yes, yes, that sort of thing. That's the binomial, that's the situation the binomial distribution appears in. And what it is in this case, x would be 3, for example. 3 times it happened out of 5. The Poisson distribution counts the number of times an event happens in continuous time or space. In a time zone or in a space. And so it's like, here is continuous time, and there's several of them that happen along the way. And this is x equals 5 by the look of it. And one of the students yesterday said a very nice thing that they didn't realize they were saying at the time, but it was a very useful thing, is that the distinguishing between them is the way that you're watching. In this one, you watch continuously and see whether it happens. In this one, you only watch at specific times. You watch at specific moments to see whether the thing happens or not in the binomial distribution. Whereas in the Poisson distribution, you watch continuously for a while and see whether it happens or how often it happens. The Bernoulli distribution, you watch once. So you count whether an event happens at all. And so with the Bernoulli distribution, it either does happen or it does not happen. That's it. So theoretically, a Bernoulli distribution doesn't produce a number. It just produces the words yes and no. But you say that this counts as 1 and this counts as 0. So the Bernoulli distribution is just a very fancy word for did it happen? And how likely was that? The binomial distribution is how many times did it happen, but I only watched at specific moments. The Poisson distribution is how many times did it happen, but I watched continuously. Yeah. I'm hoping that helps to distinguish between them. That's the choice. I choose not to go into further detail about all of these distributions at this time, but there are some further choices that we need to make with these, especially for the Poisson. It's really important to know how long you watch for or how much space you're looking at. I've been asked, is F used for two-way ANOVA? F is used for all the ANOVAs. Also used during regression along the way. F was also used for lots of other things, but specifically it's used for ANOVAs. Anytime where you're comparing the variation from one thing to another, that's what an F is for. So, okay. So I just want to do an example here. Lightning strikes during a storm with 2 strikes. No, just a second. 1 strike every 5 minutes on average. A probability of 10 strikes in half an hour. B, probability of no strikes in 10 minutes. The reason I'm putting this in here is that you have decisions to make to decide if things are Poisson distributions to begin with and to describe exactly which Poisson distribution you've got. So I know this is a Poisson distribution because I'm counting how many times something happens. 10 strikes. I've counted how many times something happens, and I am watching it for a continuous amount of time. That's what the Poisson distribution is for. To be fair, there are probably other ways to model this, but the Poisson distribution is the only one that you've been taught about in this course. And they will explicitly say this is modeled with the Poisson distribution. Yes? I said in 30 minutes, but you would have to imagine the situation. You are thinking about, well, it could happen anywhere in there. It doesn't happen. If it happens 10 strikes, that doesn't mean it literally happens specifically at every 3-minute mark. Good question. So it's useful to know that they're not all equally spaced necessarily, and that helps you to know that it's continuous. And just to be sure, between any 2 strikes, there could always be another one. Yeah. Great. Thanks for bringing that up. Very useful. So these are different distributions because they are counting things in different situations. The grand situation of lightning strikes over time is the same, but because the time frame I'm looking at is different, I expect different amounts of lightning strikes. And so the probabilities will be different. So part A there, I've got, if X is the number of lightning strikes, it will be a, do they use this symbol with a twiddle to say that something? How do they do POI, POIS? Sorry? Just PO. Sure, why not? That's so distressing because it's the OI together that makes the what sound anyway. I'm very distressed, but that's okay. I'll get over it. Poisson distribution, and in this spot, most people put the mean. I don't know how your lecturer does it. So I'm just going to say Poisson with mean. Well, how many do I expect there to be in half an hour? 6, because there's one every 5 minutes on average. And so I would be using the Poisson distribution with mean 6. And B, I'd be using the Poisson with mean 2, because there's one every 5 minutes. And so my calculations would be different in those situations because it's a different time frame and therefore a different average that I'm expecting. And just to be absolutely clear on that, and I'm going to borrow some space from over here. So the probability of that the number is 10 will be the mean. Yeah, let's give me a second. The mean to the power of 10 divided by 10 factorial times e to the power of minus the mean. That is the formula for the probabilities that go with the Poisson distribution. Pretty sure. If I had a cheat sheet with me, I would look it up. I do have the notes. Ah, that's because I'm not looking at the notes. Just a second. That there, that lambda is the mean, which is not the same as the rate. The rate is 1/5, like 1 in 5, 1 every 5 minutes. The lambda is the actual number you expect in the time frame. And so I've got the mean to the power of the number you're thinking of divided by the number you're thinking of factorial times e to the power of minus the mean. So in this one, in B, the probability that this x is equal to 2 is, not 2, equals 0, because there's no strikes, is the mean to the power of 0, e to the minus the mean over 0 factorial. If you look at this formula, the mean occurs in it twice. That's not a 10. Sorry, this is a 6. Sorry about that. Right. See, this is why I say these things. The mean is in this formula twice, and the number you're thinking of is in the formula twice as well. You would have to add them up one at a time, or ask a computer to do it. So just a second. What if it was the probability of 10 or less strikes, yeah? In half an hour. Then I would say that I need the probability that x is less than or equal to 10, which is probability that x is 0 plus probability that x is 1 plus probability that x is 2 plus probability that x is 10. If you really wanted to do it by hand, that's what you would have to do. And each of those would go with this formula, but with this number changing from 0, 1, 2, 3, etc. But it is also worth noting, someone asked earlier about CDFs and PDFs. The CDF, the cumulative distribution function, or possibly cumulative density function, doesn't matter, is the probability so far. That's what that cumulative means. It means accumulate, like added up so far. So the cumulative distribution function is the running total of what the probability has been so far of all of the numbers up to this point. And so the probability that x is less than or equal to 10 would be done with the Poisson CDF function. Now, I don't know exactly what it's called. Is it POIS CDF or something in MATLAB? Just a second. It's probably in the notes, isn't it? Okay. There it is, plus CDF x mean. Okay. So what this does is, this 10 is the point you're up to, and you want the probability of there for everything that's there and back. And the 6 is the mean. Yeah. So you could imagine an exam question where they give you some scenarios and ask you to find the probabilities and then say, you may want to know the results of these MATLAB codes. And they'll say plus CDF 10.6 and plus PDF 10.6 and whatever. So if I'm going to say, I just want to point out at this point, the probability that x is in fact equal to 10 would be plus PDF. The CDF is the cumulative one. It adds up everything so far. The PDF tells you the probability of just that one number.
And more than is totally.
Yeah, if you want greater than, you're going to have to adjust it. So if you want greater than 10, I'm saying, okay, well, my computer's only going to tell me the before and not the after. So I can say that that's 1 minus that. Good question. Okay. So here's the thing. This says strictly greater than 10. So 10 isn't allowed. And so the opposite of that is less than or equal to 10 because I have to take off the 10. But you were right. If I wanted probability that x is greater than or equal to 10, then that would be 1 minus the probability that x is strictly less than 10. But since it's a Poisson distribution, it can't be anything between 9 and 10. So that's the same as 1 minus the probability of less than or equal to 9. And so I would use the plus CDF 9. I know that's two steps in the working. It's really important to me for the purposes of getting it right that I do that move first, that greater than or equal to, the opposite of that is properly less than, and then go, oh, but I can't have anything between 9 and 10, so that drops it down to 9. If you're doing this calculation with a continuous distribution, you don't drop it down to the next one because it's possible to be things between 9 and 10. I'm going to do an example of that in a second. But the Poisson distribution only produces whole numbers. So if you're less than 10, that's the same as being less than or equal to 9. And if you're more than 10, that's the same as being greater than or equal to 11. But just be really careful about whether you can be the numbers in between or not, because that'll drop it down to the next one for a discrete distribution. And so there we go. That's another decision to make about how you deal with less thans and greater thans and less than or equal tos and greater than or equal tos. It depends on whether you're thinking about discrete or continuous distributions, which is why they give them those names, so that you have a name to hold on to help you with that process. Okay. Cool. This is not unique to Poisson distributions, of course, this move that we're making here with the CDFs. It's worth pointing out that CDFs always go with the less than or equal to. Really important. Whereas the PDF goes with equals. They both have an equals. Just want to point that out. Okay. How are we feeling about our discrete distributions? Cool. One last thing to say is that binomial distributions, you have to tell them how many times you look. That's how many trials. And the probability of success for each individual trial separately. Look at me squeezing it in. You do what you want to do in your notes. The number of trials, which is how many times you looked. And this is the probability of success within one trial. So that's not, the P isn't the probability of the thing happening once. The P is the probability if you look once that they're happening that once. So when you roll a die and you're looking for 2s, for example, the probability of success every time you roll it is 1/6 every individual time. But if you roll the die 10 times and say, what's the probability of getting 1, 2? That's a different question. Because in order to get 1, 2, you would have to have all the other ones have no 2s, and you have to take all that into account, and that's what the binomial distribution is doing. It's taking into account all the possible ways to get the number that you're thinking of, and it has a formula of its own. Cool. So one of the differences between discrete and continuous distributions is that discrete ones have a formula for what the probability is for a single number. So this one has a formula to say what is the probability of that single number all on its own. And the binomial distribution has that too. It's not this formula, obviously, but it's a different formula. And that formula is called the PDF. Continuous distributions don't have that. They have a PDF as well, but that doesn't tell you the same information. Okay. So your most famous continuous distribution is the normal distribution. And you've learned the uniform and the exponential as well. Continuous distributions, no matter which numbers you think of, there's always another number in between them that's possible. Which means that there's infinitely many possible numbers that could be produced, because you can get as far down in between the gap as you like. Well, there's definitely one between those, and there's one between those, and there's one between those, and there's one between those. And continuous distributions, there's lots of different numbers that are possible. And so the probability of any one specific number is more or less zero, because there's infinitely many options. And like 1 divided by infinity is like 0. And so you can't talk about getting a specific number. You can only talk about getting in a specific zone. You can only talk about a particular domain having a bigger or smaller probability than another domain. That's the idea of continuous distributions. And so your PDF doesn't say the same thing as the PDF does for a discrete distribution. In fact, I believe a discrete distribution, they call it a PMF, probability mass function. But MATLAB still calls it a PDF because they take the D to mean distribution. Yay. Okay. So continuous distributions, you can only talk about a domain having a probability. And when you have a PDF, I'm going to draw one that's definitely not normal. What this PDF does the official name for this is a probability density function. What this graph does is it tells you which numbers it's more likely to be near, not which ones it's more likely to be. So this number, it's more likely to be near that number than it is to be near that number, for whatever you mean by near. Like, yeah, cool. So if by near you meant within 0.01, then you could draw a little zone around here, and that probability would be bigger than this probability. So probability density function, and the areas under it are probabilities, not the heights, the areas. That's the important thing. And the density is saying how much area is there as you move past this point. How quickly is the area changing? So PDFs are literally derivatives of something else. They are the rate of change of probability as you move past this point. If you are accumulating probability from this point forwards, as you move past this, does the probability go up faster than it does when you move past this? That's why it's higher here. But most of the time, it's safe in your head to say, oh, it's more likely to be this number than this number. Just don't say it aloud or on paper to a statistician. They'll be annoyed at you. They've spent centuries, about 150 years, trying to figure out how to say this in ways that aren't wrong. My daughter's trying to do a math assignment this week. It's about probability, and God, it's the worst written assignment. But I feel for the teacher because it's so hard to write a probability assignment. not badly. Anyway, moving on. So that's the philosophy of continuous distributions, and the CDF is the same as it was before. The CDF is the sort of running total area. And so when you say the CDF, so this is normally called little f of x, and this is normally called capital F of x. And it's the probability that your random variable is less than or equal to x. But with continuous distributions, since you can go all the way up to x, like all the way up to, like if x was 10, you could go all the way up to 9.999999999, as many nines as you like. Being less than or equal to x is not really all that different from just being less than x, because you can't really be 10 technically. Well, yeah, you can get as close to 10 as you like. And so being less than 10 is the same as being less than or equal to 10, which is different for what it is for discrete distributions. But this is still the same. CDFs are always less than or equal to, and it's just easier to have that thing in your mind as a less than or equal to, and then say, cool, for discrete less than or equal to is different from less than, but for continuous less than or equal to is more or less the same as less than. So I'm just going to write that down. Discrete probability that x is less than or equal to x is different to probability is strictly less than x. They're different things. And for continuous, probability that x is less than or equal to x is the same as probability that x is less than x. I'm almost certain that this is probably the definition in a theoretical probabilist's mind of what discrete and continuous are. I could be wrong. But let's run with it. You could use this as a definition of what it means to be continuous versus discrete. Yeah. Anyway, this is just an aside that's worth pointing out. So the most famous continuous distribution of all is the normal distribution. And when I say there's lots of normal distributions, different one for every mean and standard deviation. Actually, let's line them up next to each other, like I did with the others. These are our three distributions that you've been told about. Let's just check that I've got that right. Have I missed any? Normal, exponential, uniform. Okay, cool. These are our three continuous distributions that you've been told about that exist in the wild outside of a hypothesis test. They appear as good ways of modeling real things. So, wild continuous distributions. The other ones are going to be like tame, I guess. Captive. Okay, these are my wild continuous distributions. The uniform distribution is literally saying that it's just as likely to be near any number as it is to be near any other number. They're all the same chance of being close to them. Any zone that's the same width will have the same probability. That's what a uniform distribution is. Now, I don't know if uniform distributions really exist in the wild, but it's a good guess for a distribution if you don't know anything. So uniform distribution has a bottom and a top of these are everything is between these two numbers and they all have the same probability. Not that they have probabilities of their own. They all have the same density. And the uniform distribution is great because technically it has a formula for how high this height is, but you don't need to know it. But you can figure it out. Like if this total area is 1, because it has to be 100%, the total area is 100%, and it's b minus a wide, it has to be 1 over b minus a high so that the total area comes out to be 1. Like it's this wide and this high, so that when you multiply them, it comes out to 1. So you can always figure out the height of your PDF for a uniform distribution, but nobody needs to know what that is. So this is just my example that goes with the uniform distribution, which is a classic uniform distribution example. So wait, if someone says that something's a uniform distribution, this is all you need to know, what the top and the bottom end is. That's all you need to know that. And nobody needs to look up a computer to figure out probabilities with a uniform distribution. You can figure it out. So uniform, so let's say X is uniform with minimum 10 and maximum 50. What's the probability that of X being between 25 and 35? This is just my example. All right, let me draw a picture of it. There's 25. There's 35. Somewhere down here is the 10. Somewhere up here is the 50. And we want this bit. So this area is 1, right? So we just need to know what percentage of the total area this bit takes up. And it's 10 wide out of something that's 40 wide. So it's a quarter. Doesn't look like a quarter because I've drawn my picture badly. So the probability that equals 10, that's the width between the 25 and the 35. Out of 40, that's the width between the 10 and the 50. So just so you know, this is 35 minus 25, and this is 50 minus 10. And that is it, the uniform distributions. They do have I mean, the mean is exactly halfway in the middle because everything's it's perfectly symmetrical. It does have a standard deviation. I can never remember what it is. I think it's like b minus a squared on 12 or something like that. There's a 12 in there, I'm sure. Feels like there should be at least a 3 on the bottom because when you integrate. No, I have no idea. Just making up crap. So uniform distribution theoretically happens in the wild. It's not a bad guess for how things are distributed if you don't have any information at all. The normal distribution is really quite likely to happen in the wild. Most things that you measure on physical objects are normal. Not always true. Some of them aren't, but especially living things. Most things that you measure on living physical measurements on physical things, on physical living things, will be normally distributed. Basically, anything that is caused by multiple influences tends to be normal. So the heights of people, the lengths of pencils made by your machine at the factory, the weights of ice creams made by your factory, whatever, they're almost always normally distributed. Also, now we'll get to that. And it looks like this. That's not a that's pretty good. It's supposed to be symmetrical. This one's a little bit got a kink on this side that isn't on that side, but whatever. Nobody cares. One day I'd like to have like a normal distribution template, but I wouldn't because I actually quite like drawing normal distributions. One day I want to do some research and ask people to draw normal distributions and then get like an OCR thing to read the probability and see if it's the correct distribution and see how close to normal we would get. How close to a normal distribution are people when they try to draw a normal distribution? That would be cool. But, you know, I've got plenty of other stuff to do, like revision seminars. So that's what they look like. And there's a number in the middle, which is the mean, which is called mu, which is the Greek, the lowercase letter that is the same as the M. It makes a sound in Greek, for mean. And this distance here that goes from the center to the inflection point is sigma, which stands for standard deviation. And sigma makes it sound in Greek and for standard deviation. So if you make it wider, you have to make it shorter technically, because so that the area's totals 1. But nobody really cares because like it's all percentages anyway, so you can draw them all exactly the same. They all look the same. They're just sort of wider or narrower or flatter or whatever, but the probabilities work out fine. And it's always true that the probability between like mu and mu plus sigma is always the same probability for every normal distribution. That's the basic idea of a normal distribution. So not that different from how a uniform works, in that if you've got a uniform that is this wide, and if you take the middle quarter of the numbers, it will be a quarter of the probability. Well, for normal distributions, it's just that it's more probability in the middle than at the edges. Cool. So in my head, I don't know if you've heard me say this before. If you watch any of the other seminars, you'll see it. In my head, the distributions all live in a city, and they each have a couple of parameters to tell you which distribution you've got. So with the binomial distribution, you need to know, where'd it go? Oh dear. Oh, there it is. Good thing I numbered them, hey? With the binomial distribution, you need to know the n and the p. And different n and different p will give you a different collection of probabilities. And so it's like the n is the street number and the p is the house number in binomial gardens, the suburb where the binomial distributions live. And the Poisson distributions, they only need one number to tell you where they live. Okay, normal distributions need 2, a mean and a standard deviation. So you go to the mean, the house with the mean, the street with the means, and go along there, and you've found the house with the standard deviation. And every time anyone calculates, anyone measures anything, you knock on one of the doors and ask the normal distribution to give you a random number, right? That's pretty much how it works. And one of those houses is the one with mean 0 and standard deviation 1, and that's the standard normal distribution. So standard normal. And it is usually called Z. I don't know why Z. Presumably it was the next letter available after X and Y. Maybe it's like from German for number, like Zahlen. I put a cross on my Z so you can tell it from a 2. But I do, this is extremely silly. This is very silly. Ready? The normal distribution. There you go. No good reason, but I like it. Okay. And it's called Z. And it's called Z because it comes up when you do hypothesis tests. And you need to have a letter to stand for your test statistic. And so we're going to call it Z. And over in psychology, they just love a good Z score. And a Z score is how many standard deviations away from the mean are you? So if you had something with mean 10 and standard deviation 3, and you had an answer of 6, you'd go, okay, cool. That's 4 down from the mean. And so it's like minus 1.3 standard deviations. And so you can measure on a normal distribution how many standard deviations from the mean are you, and that's how you figure out the probabilities. And that's exactly what the normal distribution, the standard normal does, because the standard deviation is 1. So your distance from the mean is how many standard deviations away you are. And if it's positive, you're above the mean, and if you're negative, you're below the mean, because the mean is 0. And so that's the thing. And it turns out for any normal distribution, if you take off the mean and divide by the standard deviation, then what you're doing is you're saying, how far from the mean am I, and how many standard deviations is that worth, and therefore what you end up with is a Z. This is called standardizing. I don't know if it's important, but it's worth pointing out. So back in the day, let's consider Fisher in 1925 when he invented hypothesis testing. Before computers were even a concept, how would you figure out normal distribution probabilities for random normal distributions with random means and standard deviations? You couldn't. What you could do is you can convert them all to Zs and have one list of probabilities that go with the Zs. And that's what they used to do. They'd have a standard normal distribution table, and they convert everything to Z so that they could figure out the probabilities. Economists in their first year statistics course still do this. Even though Excel, just Excel, not anything fancy, is perfectly capable of figuring this out. Anyway, so there you go. Cool. So, I mean, yeah, if you've got a computer that can do normal distribution calculations, you can find the probability of being between anything and anything else, as long as you say what the bottom end is, what the top end is, and what the mean and standard deviation is. But your computer will only tell you left-hand sides again. So just as an example, I'm going to have to take up some of the exponential distribution. This is part of the normal distribution. X is normal. Mean 10 and standard deviation 3. What's the probability that X is between 6 and 9?
Okay.
No, let's do not do 9. 6 and 11, just some random numbers. Well, that's this area. There's the mean there. And 6 is about here-ish. And 11's about there. And we want this bit. So the X's we want are here. And the area that goes with them is this bit. And that's what we can get. Unfortunately, your computer can't tell you, your MATLAB won't tell you that directly. A good graphics calculator can tell you that directly, but MATLAB won't. MATLAB will only tell you everything to the left. And so you have to go something like that. The entire thing less than or equal to 11 minus the bit less than 6, and that's the bit I want. So the picture in my head is this bit, that's this bit here, and yellow it is then. And this bit, that's this bit here. And so that with MATLAB would be norm probably, CDF. 11, 10, 3. Could be wrong about the 3. They might want a 9 there. Almost certain it's a 3. I will have to just look that up. That's bad form if I don't look it up. Just a second. Yes. Okay. Cool. It is. I was right. It is the standard deviation. That's the first bit, and then the second bit would be minus norm CDF 6, 10, 3. And then your computer would tell you an answer. I'm pretty sure that the answer will be about 0.4. That's my guess. The reason I know this is that a normal distribution, the zone between the mean and one standard deviation is about 34%. And we've got a bit more than that. So I'm going to go 40% and we'll see what happens there. Okay, cool. The exponential distribution is most interesting. It measures how much time there is between events. It measures the time until an event happens. So it's the same scenario that the Poisson distribution happens. You're just measuring something else. If you look at a particular time frame and you go, how many events happen in that time frame? That's a Poisson distribution. If you look at a particular, that same situation and you just watch and wait until an event happens and go, what time is it now? That's the exponential distribution. So they call these things Poisson processes. But a Poisson process can be measured in multiple different ways. You can count how many times the event happens. You can count how many times the event happens in this zone and this zone and this zone and this zone of different widths, and you get all these different Poisson distributions because you're all counting things. But if you measure how much time there is from anywhere until the first event happens, that is an exponential distribution. Yep. And the exponential distribution is one of the few distributions that have a formula that is actually easy to remember and calculate with. The CDF of the exponential distribution, it looks like this. It's much more likely to have a shorter time than a longer time. The longer you wait, the more likely it is for an event to have happened by now, basically. So the probability of waiting for an extremely long time is less than the probability of waiting for a less extremely long time. So yeah, so the further you go, the less likely it is to have to wait that long until the event happens. And they go down at different speeds depending on how often your event happens.
So where does it start on the y-axis?
0. Oh, where does it start here? I can't remember. I think it's
Like, it's not like the event.
no. Well, this is time here, and this is the time that the event happens.
Mm-hmm.
And this axis here is the probability density, right? Yep. So if you pick a random time, go 10 minutes, what's the probability of the event happening by now? That's what an exponential distribution would do. Yeah. Cool. Yeah, you're more like doing areas usually, but yeah. So the height of this curve, I can't remember what that is. It does have a value. There's a formula. It's got an exponential function in it. That's why it's called the exponential distribution. But I do know the formula for the area on the right-hand side. So this area here which is the opposite of the CDF, that area there is e to the minus lambda t, where lambda is the speed at which the event happens. So lambda is the rate. So as an example, lightning with 1 per 5 minutes on average. What's the probability that you wait for. There we go. Next page. Don't squeeze it in, David. All right, let's just do this example. Lightning strikes about once every 5 minutes. Probability that you're waiting longer than 10 minutes to see one. Okay, so this is still the same situation as before that I had with my Poisson distribution, but I'm not counting how many lightning strikes happen. I'm waiting until one of them happens and measuring the actual time itself. So time is continuous. Given any 2 times, there's always another one in between that is possible. So that's the clue there. It's continuous, and I'm measuring a continuous thing. So that's an exponential distribution. So if x is the time until a strike, then x is distributed according to an exponential distribution with rate 1 every 5 minutes. They usually call that lambda. Pretty sure could be called rho or mu, but lambda sounds like thing. And so the probability that x is more than 10 minutes, I've got 2 approaches here. One approach is to straight up use the opposite of the CDF, which is e to the minus a 5th times 10. See what I wrote here, e to the minus lambda t. That is it. The probability beyond a particular number is this probability. So e to the minus 2, whatever that is, it's about 0.1. No. So you could do that. So I know that I said that you need CDFs, and the CDF is the left-hand side, but for the exponential distribution, the right-hand side is easier to remember. The left-hand side is 1 minus that. And, or, like that. The probability of being greater than 10 is the opposite of the probability of being less than or equal to 10. And I could use MATLAB to do my exponential CDF 10 1/5. Let me just check if that's the correct code. Oh, for the sake of fuck. MATLAB uses 1 over lambda because reasons. Okay. Good to know. All right. So just be careful in MATLAB. Oh. The problem with all computer programming languages is that they're all built over a long time by lots of people, and they all have different opinions about things. And so you end up with this sort of weirdness going on. It's funny because it makes perfect sense to me that the Poisson should have the opposite parameter. Like the Poisson is how many you would expect, and which is the opposite of how long to wait. And so it makes sense to me that one of them is the 5 and the other one's the 1 over 5. but obviously the MATLAB writers didn't think so. So there you go. So that's just going back to things. There was a decision here. Which of these is it? It is almost always true in the assignment and exam questions that you were given that they will tell you what the distribution is. And if they don't, it's probably an exponential distribution. But only because that's the only one they've given you, right? If they gave you more information about the sorts of distributions things have, if they said, oh, well, the sizes of particle grains in sand is a log normal distribution, and they taught you about the log normal distribution, you'd use that. But they didn't tell you that. But just know that if you're doing materials at some point in the future, the log normal distribution will appear. So that's how to decide those things. And I'm going to continue talking because I really want to finish this. The other distributions are the ones that appear in hypothesis tests. And there were 3 of those, 4 of those. I shall call them captive. I will not be offended if you leave. Hypothesis tests and confidence intervals. Okay, so there's Z, which we've seen already. It has the wonderful, enjoys the wonderful property of being both a wild distribution and a captive distribution, like a pigeon. We've already seen Z. There is T, there is chi-squared, and there is F. Okay. The thing is, each of these distributions appears in multiple different places. And the reason that is because statisticians designed their hypothesis tests specially so that they could use these distributions, because these are the only ones they knew about in 1925 when Fisher wrote his book. So these 2 were known. Normal distributions have been known for quite some time, a couple of 100 years. This one, maybe 1850s. This one, 1900-ish. This one, 1925. It's in Fisher's big book of stats for agriculture. I can't remember what it's called, the book, but that's what I call it. So they're all that, other than this, these are all invented in about a 50-year period, or discovered, depending on what your philosophy of mathematics is. But this existed first. Because normal distributions, they just noticed them. They went, oh, well, look, everything's like bell-shaped, cool. And they did some calculus and went, this is a pretty good approximation to that. And so, cool. In hypothesis tests, you're asking yes or no questions, and you're attempting to answer yes or no questions. Every hypothesis test goes with a yes or no question you're trying to find the answer to. Confidence intervals answer what is this number sorts of questions, saying, I want to know what the mean is for this population. And they give a range of possible answers. Okay. So the philosophy of all of this is that you go, well, what if the answer to my yes or no question was no or yes, whichever of them is the most convenient? How likely is what I've seen to happen? Because if it's really unlikely, maybe I don't believe that hypothesis. So it's like a proof by contradiction, but with probabilities, which makes it spicier. But that's the idea. And because we're going to calculate a probability, we have to have the distribution of something, because you can't calculate any probability without knowing what all the probabilities are. And a distribution is a description of all the probabilities. So You're in some situation, you've got some data, you're asking a yes or no question, you're wondering about one of the answers and going, hey, what's the probability of my data if I lived in that land where that was true? Crap, that's hard. What if I did this calculation? Would I know what the distribution of that was? What if I did this calculation? Would I know what the distribution of that was? Aha, this is a good one. If I did this calculation, the distribution is a t, and I know what the formula is. Well, I can calculate that with some severe work or a computer. So, cool. It turns out that if you measure anything on one thing, and you find the sample mean of several of those measurements on n things, then if this is normal, then so is this. I'm just going to put a bit of space here. So if you measure x on one thing, and this is a continuous variable, actually it doesn't matter, but anyway, continuous variable, and it's got mean and standard deviation. If you do x bar, the mean of n things, then that's also normal, and it has a mean of mu still, and a standard deviation that's a bit smaller. And just very importantly to point something out here, this x is all of the things that could happen if I measure one thing. I imagine all the one things and all of their measurements and how likely they all are. This is all of the means that could happen for all of the possible groups of n things. The big philosophy of distributions is that everything has a distribution. Anything that you could measure or count on one or multiple things has a description of what the probabilities are, whether I know what it is or not. Somewhere in the fabric of the universe, there is like I don't know, an angel or something with a great big book. And every time anything happens, they go, oh, yes, the distribution's a normal distribution. And right, cool, here's your random number. And so that's the philosophy. So when you do hypothesis testing, you've only got one mean, right? You've only done it once. But you imagine all of the things that could have happened, and you compare it to that. And this is all the things that could have happened for a sample mean. And that's fine, but it just doesn't feel very standard. I would like a standard approach that everyone can do and feel like they're really doing something. And so I will standardize, and I will have x bar minus the mean on sigma on root n, and I will get a z, because that's exactly how you make a z. You subtract the mean and divide by the standard deviation. So this is the original hypothesis testing concept, even before they started to be called hypothesis tests. So before Fisher, this is what people were doing and doing calculations. Nobody had called the probability you get at the end a p-value yet. And they were doing this. And that is why people teach you this, even though nobody does it anymore. Because it's part of the history. So what that means is this is the big philosophy. And this is the standard normal. Well, we know what Z stands for, so that's okay. That's the big idea that everything else was trying to do. I hope that helps. So what that means is if you have a mean that you've measured and you're pretty sure that you know what the standard deviation is, and you're wondering if the mean, if the true mean is mu, then you can do this calculation and get an answer for Z and look it up in a Z table and get a p-value. So this is why you say, if the question is the true mean equal to mu, and you also know what sigma is, then you'll use a Z. Oh no, there's another place the Z turns up. So unfortunately, I'm going to need to have a whole extra row of my table in a minute. But I'll come back to that in a second. So that's it. Is the true mean equal to mu? If that's your question, and you also know what sigma is, then you'll use a z, and it will be this calculation here. But if your question is the true mean mu, and you don't know what sigma really is, and you have to estimate it from your sample by using the sample standard deviation, is the true mean mu, but you don't have extra information about what sigma is, then you'll use a t. And that t will be x bar minus mu over s on root n. And Gossett, who worked for the Guinness Beer Company, figured this out in about 1905-ish. I don't know any of the exact dates, sorry. There's like a 50-year period from 18-something to 1930. So that's your first decision-making process. I find it very useful to focus on the question that's being asked, not on the null hypothesis. You can always create the null hypothesis from this situation. The null hypothesis is always the answer to this question that goes with the value being a specific number. So the question is the true mean equal to mu? The null hypothesis is the true mean is mu. It's traditionally mu naught, right? The note that goes with the null hypothesis. Yeah, is the true mean equal to mu naught? Cool. The answer to that question that has one answer is mu equals mu naught. Mu is not equal to mu naught has lots and lots and lots of answers, and so that can't be the null hypothesis because I have to make a choice to do this calculation. So that's your first one. So you can understand why this never happens because no one ever really knows what sigma is. But you're learning the history of the theory, and so you have to know. Okay. They're the two main questions. But there are other questions you could ask about means. Is the mean in these two situations different? Or possibly, is the mean in these two situations the same? It's the same question. The null hypothesis will be that they are the same because there's only one way to be equal. And in that case, you will also calculate a t. But this time your t will be like x1 bar minus x2 bar on some wicked thing with the square root. So you will notice they give you a table and recommend that you put it on your cheat sheet in this course for statistical procedures. It's somewhere in the notes. And it has estimate, hypothesis, standard error. And it will have like, this is the estimate, this is the hypothesis, and this is the standard error. And you construct your t from those calculations. That's what they're talking about in that table. Yes, the computer's reminding me that the Maths 1A seminar starts in 15 minutes, but we'll all be okay. I just want to point out the difference between these two stories. In this story, I'm just asking about one number. I only have one situation. I have one number. What is that number? Is it equal to a particular mu naught? In this question, it's like, I've got two different situations, and I want to know whether the mean is different in those two different situations. That's this one here. It's all about the question that you're trying to answer. Pardon me. Okay, but wait. There's other places where a t occurred, and they called it paired, match pairs situation, maybe? Paired t-test, something like that. Match pairs. The thing is, It depends how your data is organized, whether you do this or the other one. This one goes with the situation where the objects under study are just, there's different objects in one situation as there are in the other situation. So the situation, this one actually goes with different situation is different objects. Like, yes, you've got two different factory machines. You measure the things on this machine and you measure the things in this machine, and they're different things. Okay, I'm going to change colors so that you can see the difference here. We have a question here. It still is the mean different. Different in these two situations. But this time, different situations is the same objects twice. In that case, you do a whole different calculation entirely. And it is in fact this calculation again, but on a new data set. You calculate D and you do the average of the differences, and you wonder whether they are, the mean of that is equal to 0 or not. So you calculate the difference for every pair of objects and go, well, if the mean is not different in these two situations, then I'm really going to put this H naught, the mu of the D is 0. That's normally how it's written. And you have the standard deviation of the Ds on root N. And that's the match pair situation. So now we have another way to distinguish between things. We have the same question. Does this situation make a difference to the measurements that I have? But it depends how your data is arranged. Different situations, different objects, do this. Different situations, same objects twice, do this. And I find for myself that that's the easiest way to say it in my head, to be able to distinguish between them, because they say matched pairs or whatever, and go, what? The pairs they're talking about is the pair of measurements for each object. That's what they're talking about. So, yeah. Chi-squared happens when you have a question about, is the chi-square test in this course?
Yes.
Fun. What? You have the goodness of fit chi-squared test, and you probably have the association chi-squared test, don't you? Cool. Fancy. Okay. Chi-squared test is not about measurements on individual things. So in this one, it's like, is the true mean equal to mu? I'm measuring stuff on every individual object, and I'm calculating averages. Chi-squared test is a whole different situation. Instead of calculating averages on based on groups, and everybody's got a number and you do average based on those numbers, in this time, the information about every object is just which category is it in. And you want to know whether the categories are whether the objects are distributed across the categories in a certain way. So, question. I don't know how to say that. Do things go into categories this way? That's your question. And you have a table like A, B, C, D, or red, yellow, orange, or agree, disagree, neutral, or whatever. And you say, do I think they're all equally likely? Or do I think that this one's twice as likely as the others, or whatever? And you can decide if the things go in categories this way, and that is the chi-squared for goodness of fit. And it's a different chi-squared distribution as it is with this one. Oh, crap, I didn't put it in there. This one has a different degrees of freedom as this one does. The t-distribution, crap. The t-distribution has a number called its degrees of freedom, which tells you which t-distribution it is. In a distribution city, the t-distributions all live in a tower block, and that's the button you press on the lift to get to the right one. Yeah, and it's worth noting that the z-distribution is the t-distribution, but with infinity degrees of freedom. It lives on the infinitieth floor, like Lord Business in the Lego movie. Yeah. Lord Business in the Lego movie is the standard normal distribution. Which actually makes a lot of sense based on the plot of that film. Anyway, you can tell I've been talking for too long. The chi-square distribution has a degrees of freedom as well, which tells you where the chi-square distribution lives and which one it is. The F distribution has 2 degrees of freedom. To tell you which one it is. It has 2 addresses. There's a street and a house number. And that's because in the theory behind it, it's made from 2 chi-square distributions divided by each other. So with the chi-square for goodness of fit, you have all these boxes that your things can be in, and the degrees of freedom is how many boxes except one. Running out of space here. So that's that question. I'm sorry, the color coding is not coding. It's just different. Sorry about that. The other question with the chi-square test is, does being in one category make it, being in one option, which option you are in one categorical variable make a difference to which option you're in for the other one? So are these 2 categorical variables related? And the official stats word for related is associated. So, but that's the question you're asking. And it's also a chi-squared test. It's the chi-squared test for association. Sometimes called the chi-squared test for independence. I don't know which one is used in this course. Possibly both. They're the same. And in this case, there's 2 categories, right? There's like a 2-way table of options for what things could be. Like you've got A, B, C, and, you know, or red, yellow, blue, and green or something. Oh, maybe we should do purple because it's the wiggles, right? Blue. So the degrees of freedom is you cross out one row and one column, and it's the number of boxes left. That's the degrees of freedom. Yeah. And the reason it's called degrees of freedom in this context is that if you kept the totals, like the grand totals along the column extras here, you've got a total column and a total row. If you kept the totals the same and you change the numbers in these boxes, then you wouldn't have any freedom to change these because they'd be figured out from the other ones. And the F distribution happens when you do ANOVA. That's when it happens. And I believe that degrees of freedom 1 is the number of situations minus 1, and degrees of freedom 2 is the number of individuals total for everything minus the number of situations they could be in. I'm calling it situations. Most people call it groups, but situations makes more sense to me. Yeah. And the F distribution looks from a distance like a chi-square distribution. It looks something like that. Yeah, and so there's all these technical details, but I'm hoping that putting them all on one page, and I still have got some Zs to go, so you can see where the situations they happen in, and that's how you decide. You look at the situations and you go, am I in this situation? The ANOVA is the same situation as this t-test. It's just that there's more than one mean. So it's like, damn it. The question is, does the category make a difference to the number? To the mean, basically. That's the sort of question that you're asking. It's just that there's more than two categories over here. So does the category, does the situation make a difference to the mean? So last one, and I've got 3 minutes. More Zs. Ugh. Interestingly, the information I've given you here is actually quite enough to answer all of the questions that you've been asked, that you are going to be asked. The situation of, do things go into categories in this way? You can answer with the chi-square test. But if there's only two categories, then everyone that's not in one category will be in the other one. And so you can cut down on the work just a little. So the question is the probability... That's all right. Sit down. I'm still going on the previous one. Is the probability of being in this one category this number? What that means is like, is P equal to like, 0.6, for example. That's the sort of question that you're asking. That's the same question of, do things go into categories this way? We're saying, is it 60% this and 40% this? But this is focusing specifically just on one category instead of thinking about the two. In that case, you will do a Z. Because the binomial distribution has the tendency to look like a normal distribution. And the binomial distribution counts how often an event happens, like being in a category. And so it's all connected. And so this would be, just a second, P hat minus the P from the null hypothesis square root of, I'm pretty sure that's it. Yes. And there's another Z. Does being in these two situations make a difference to how likely it is to be in this category? Like that's really hard to say, but these two situations make a difference to how likely this category is. And so the null hypothesis goes, aha, the two probabilities are equal to each other. The picture in my head is this. You end up with a table like this, and you've got like situation A and situation B, and you've got the thing happens or the thing doesn't happen. That's a very chi-squared for association situation. And so officially, you can totally use the chi-squared distribution question. You can use the chi-square test for this question, but you can also say, I don't really care what happens here, and I just have these numbers and how many there are in each group. There's an N1 and an N2. And so what you can do is you use a Z again, and it's like P1 hat minus P2 hat over something with lots of square thing under a square root. You'll have to look that up. I can't remember what it is. It's probably this No, I have no idea. There's something. So these two Z tests are the same situations as the chi-square test. It's just there's only two options, and you're only looking at one of those options. And they are, again, a historical thing. This was invented first, and then this was invented later. But also, this feels more like the t-tests, and so it makes a lot of people comfortable, because the chi-square test feels a little bit like observed minus expected squared divided by expected. What the hell? Whereas this feels very much like the t-test and fits neatly into that table that they give you, whereas the chi-square test doesn't fit neatly into the table. So I think that's all of the distributions in all of the situations they appear. Thank you very much, and good luck. See you, everybody.